and gentlemen, today's class recording has begun. So, as we discussed earlier in the year, in case you don't remember, I'll remind you of it. We decided, or I decided, you didn't have much of a choice in this decision, I did it, that the way I was going to structure this class was to start big with observations that we make every day because of objects that we see. Basketballs and cars and trains and people, okay? Which, the way I sort of see it, is how science started, right? We ask questions about things that we see. So first thing we do is we ask questions about, people walking, and well, the ancient Greeks didn't know about basketballs, but, your experience, probably has that, right? So, but those just motion of everyday things. And we start trying to figure that stuff out. So first we describe it, and that's what we did with mechanics. And then last chapter, with forces and Newton's laws, we tried to explain it a little bit more. Well, why do these things happen? Why does something move at a constant velocity? Why does something speed up? Why does something slow down? Etc., etc. So this chapter, we get into a little bit more of that why, but talking about it from a different perspective. And so we're going to use this chapter to talk about energy and work and how that affects the interaction of objects with each other. Okay? So, energy is a term that I'm assuming you guys have heard before and that you've used before. But here in science, it means something specific. And if you read your book, it's going to give you a definition of energy that I don't like. And I'll tell you why I don't like it. All right? In a couple of days. I won't tell you today because it won't make sense to you today. But in a couple of days, I'll tell you why I don't like the definition that most books give for energy. So let's talk about energy. Okay? So, get ready, because this is probably the first of like 500 times that you're going to hear this statement, okay? Just because it keeps coming up over and over again. If you remember, maybe you do, maybe you don't, on the second or third day of school, we talked about some of the big ideas of physical science, those thematic ideas that go through all of our study of science. Energy is one of them. We are going to apply energy basically to every unit that we move on, that we go on moving forward. It's going to come up in some way, somehow. Okay? So, what is energy? Here's the definition that I like to use. Energy is the ability to do stuff. Now, I know that doesn't seem very scientific, but because it is a big foundational idea, we need to be able to apply this definition to a lot of different situations. And so the ability to do stuff is a pretty open-ended general description, but we'll see how it applies in lots of different situations. What does do stuff mean? Well, the ability to move or change matter. The ability to move or change matter. We've discussed this definition, or this description, the ability to move or change matter. We've actually discussed that a little bit as we've gone along. That sounds kind of like the definition of what? We change something. What is that? Acceleration, right? That's what acceleration is, changing the velocity of an object. So energy and force are related. Force is sort of the vehicle that energy works through, right? And we'll explore that relationship a little bit more as we go along. So, energy, the ability to do stuff, the ability to move or change matter. But what we'll see is that ability to move or change matter comes in a lot of different forms. So let's give a brief description of those forms here, and then we'll talk about one form in much more detail as we go along, all right? The SI unit for energy is joules, named after James Joule, who did a lot of work with steam engines back in the late 1800s. Capital letter J. Joules is a derived unit, and we will talk about what combination makes up that derived unit as we go along, but just know that all energy, regardless of its form, comes in joules. Okay? Good there? All right. So, first, Mechanical energy. Mechanical energy is the type of energy that you are familiar with most often, that you interact with most often. Mechanical energy is the energy associated with the motion and position of everyday objects. And when we say everyday objects, the kinds of things that we've been talking about up until this point. Basketballs, people, cars, trains, planes, things like that. So mechanical energy is the energy associated with the motion and position of everyday objects. Okay? We will talk about mechanical energy in much more detail. This unit is about mechanical energy. So I'm not going to spend a whole lot of time on it right now, because we're going to talk about it in way more detail as we go along. Okay? So even though there's a couple of spaces left there in your slide, let's move on to the next one, because we'll talk about that mechanical energy much more in the next couple weeks. All right? So next, thermal energy. All right? Thermal energy, for you guys, probably known as heat. Right? But what does the heat tell us about an object? We learned this before. Things that are hot mean what is happening. Molecules are maybe not splitting apart, but moving much more often, right? So thermal energy is the energy associated with the movement of the microscopic particles that make up an object. And those microscopic particles can come by one of two names. Could be an atom, or it could be a molecule. And we will talk about the distinctions between those things as we get a little bit more into chemistry in the second semester. Okay? So this energy associated with the movement of microscopic particles. If those particles move more, they have more thermal energy. If they move less, they have less thermal energy. Like we said, energy is the ability to do stuff, right? Anybody ever like been tea kettle on the stove or something like that, and you reach over wrong and you get a burn from the steam that comes out of it? Right? Steam burns hurt a lot more than just hot water burns. Okay? Why? Well, what do we know about the energy of particles that make up a gas? I think you guys probably know this, right? What do we know about the particles that make up a gas? What are they doing? They move. How fast do they move compared to other states of matter? A lot faster, right? They have more energy because they're moving more. And that's why a steam burn hurts more than a hot water burn. Because those particles have more ability to do stuff, like hurt your hand. Okay? Good there? All right, next. Chemical energy. We'll talk about chemical energy a lot more in the second semester, but energy stored in the chemical bonds of a compound. I think most of you are probably familiar with the idea of atoms and compounds. I think you've probably learned about that before, right? So atoms can join together to form new stuff, and we'll talk about that process way more later in the year. But when they do, they form a chemical bond. That bond has the ability to do stuff. So when we break apart atoms, the energy that was holding them together is released. And now we can use it to do other stuff, right? As Joe sits here and eats his goldfish crackers, right? The example that you interact with most often with this is food. The food you eat is a bunch of molecules that are atoms joined together in molecules. And your body breaks down that food, and when it breaks down that food, it turns that chemical energy into walking around the classroom in the middle of class, or walking from classroom to classroom, or whatever it might be, right? Your body takes that energy. You could have hold on to that until the end. So chemical energy stored in the chemical bonds of a compound, right? Next, electrical energy. Electrical energy is the basis for our modern society, right? Energy associated with electrical charges. And we will talk more about electrical charges in the next semester. But I think most of you know that if we have two positive charges, what will they do to each other? repel each other, right? If we have a positive and a negative charge, what do? Attract. As those charges repel and attract each other, they have the ability to do stuff. And we can use the motion of those particles either repelling or attracting to do something with it, like turn the little blades in your blender and make a smoothie, or make your remote control car go forward, or fly a drone and chop your finger off, or whatever it might be, right? And then try to pitch in the playoffs, whatever, you know. So as charges are attracted or repelled, they can move or change other objects, and that's why it's energy. Okay? Good there? Now, not to be confused, we also have electromagnetic energy. Sounds similar, a little bit different. Electromagnetic energy is energy that travels through space as waves. Alright? So, right, pretty much everything that happens here on Earth is driven by one energy source. What is that one energy source? The sun, right? The sun pretty much drives everything that happens here. We're not connected to the sun, but we get energy from the sun by the waves that travel through space and get from the sun to here. We don't have the sun, there's no ability to, quote unquote, do stuff here on Earth. It pretty much drives everything that we do here. Okay? Good there? Right? And then that we can also turn that into, like, you know, X-ray machines and radio waves that your cell phone works on and all kinds of things like that. That ability to do stuff transferred through space. Okay? And finally, nuclear energy. And like its name suggests, it probably has to do with what? The nucleus, right? So energy stored in the nucleus of the atom. And as we learn more about atomic structure, we will find that the nucleus of an atom is actually a very high energy location. And we'll talk about why that is. And if we can harness that energy, that ability to do stuff, we can use it to power a nuclear power plant, make electricity, or destroy Japanese cities. Wow. That's what happens. That's not me pontificating, that's telling you history, right? We harness the energy that's associated in the nucleus, and we can destroy things if we need to. Not that I'm saying we should, but we could. And we have. We shouldn't do it anymore, but we have in the past. So. Jack, do you have a question, or are you just kind of...
No.
Okay. All right. Are you sure? Yes. Everything is made
So
up.
atoms are smaller than cells?
Yes. So atoms are the smallest, well, we'll learn that atoms are not really the smallest piece of matter that's out there, but they're the smallest piece of matter that we can basically build you with. And so everything else is kind of like building an atom. So we'll get into that more as we go along. So yeah, atoms are way smaller than cells. So, all right. This unit, though, we're going to focus on mechanical energy. And like it said in our definition, right? First, switch over to the outline now, okay? The beginning part of the outline should look pretty familiar because it's the same as the beginning part of the previous one, right? So, energy, the ability to do stuff, or the ability to do damage, or the ability to move or change other objects, right? Pick any definition that you want, or write them all down, because they all basically say the same thing, right? The ability to make things different than they were before, okay? Force is how we make things different. Energy is the ability to make things different. Does that make sense? You can have the ability to do something and not actually do it. And that we'll talk about that as we go along. Okay? Good? Got all this stuff? Alright. So, today, mechanical energy. So we just talked about that mechanical energy is the energy associated with the motion and position of everyday objects. And when you are introduced to energy back in 5th grade or whenever we first start teaching you that, you learn about 2 types of energy, right? What are the 2 types of energy that you learn about in 5th grade? Kinetic and potential. That's what goes on here, all right? So mechanical energy is the total amount of an object's kinetic and potential energy. And we'll talk about that there are different types of potential energy. We'll talk about what potential energy is and why there are different types of it. So the total amount of an object's kinetic and potential energy. Good there? All right. So let's talk about kinetic energy. I'll save that slide for the end. All right. I'm sure that you've heard of kinetic energy before. And kinetic energy is always defined as energy of what? Movement, right? Or energy of motion. And that's what kinetic energy is. Because something is moving, it has the ability to change other stuff, right? Kinetic energy depends on 2 things. It depends on mass and it depends on speed. Yes. Yeah, number 3. You're writing that equation down in number 3. So KE equals 1/2 mv squared. Yes, Jeff?
I have a question about a question on this. Yes, can I ask it?
Yeah, everybody's seeing this. Hold on. Pausing. Ladies and gentlemen, recording has resumed. So, kinetic energy depends on mass and speed. Let's talk about the relationships. Okay? First, mass. Mass is over there on the right-hand side, right? If we double the mass, what's going to happen to the kinetic energy? Well, it's going to not speed up. It's going to, well, if we double the right-hand side of the equation, what has to happen to the left-hand side of the equation? It's got to double. Why? Because what does an equation mean? Equal, right? So if we double mass, we double the kinetic energy. What kind of relationship is that? It's a direct relationship. But now let's look at speed, right? V. If we double the speed, right, we make it go twice as fast, mathematically, what do we have to do to speed in that formula? You're squaring it, right? So if we take v from 1 to 2, right, 1 meter per second to 2 meters per second, how much does the right-hand side of the equation actually go up? By 4. Do we understand that? Right? Do I need to draw it on the board, or are we picturing that in our head? If you want me to draw it, I'll draw it. All right. So that means that if speed goes up by a factor of 2, the kinetic energy goes up by a factor of 4. Okay? Yes, no, maybe? If we make velocity 3, right? Now we go from 1 meter per second to 3 meters per second. Mathematically, what are we doing to velocity on the right-hand side? You're squaring it. So the right-hand side, if we go faster, doesn't go up by 3. It actually goes up by 9. Why 9? 3 squared, right? What kind of relationship is that?
Quadratic.
It's a quadratic relationship, right? So, kinetic energy depends on mass and speed, but it depends on them differently, right? So, what happens to the kinetic energy of an object if its mass is doubled? What do we say happens there? Kinetic energy doubles as well, because there is a direct relationship between mass and kinetic energy. Okay? But what happens to kinetic energy if its speed is double? It quadruples, or it goes up by a factor of 4. Because how are kinetic energy and speed related to each other? Quadratically. Right? Speed is squared in the formula, and we talked about that is a quadratic relationship. Right? So, let's apply that to a situation. Okay? In a couple of years, well, maybe some of you, maybe at the end of this year, depending on how old you are, you're going to get your temporary license. All right? So, let's say, finish writing this, and then we'll talk about what this means. Go ahead and finish writing. Might be a good idea that while you're writing down the answers to these questions, you throw in some terms that I haven't included in these descriptions, like direct relationship and quadratic relationship. Like, might be a good idea to throw those in there. Mass and kinetic energy have a direct relationship. Velocity and kinetic energy have a quadratic relationship. So let's talk about what this means, okay? So let's say the afternoon after you've received your temporary permit to drive, you beg and beg and beg your parents to let you drive the car. So you decide, okay, I have to go shopping, I have to go pick something up at Cracker Park, so we'll go to Cracker Park. Okay? Let's go Giant Eagle because, your parents would be crazy if they took you driving at Cracker Park on your very first day of life. So you go to Giant Eagle, right? And as happens, right? So driving through the parking lot, 10 miles per hour, you hit a little car. Okay? So 10 miles per hour, right? Not a whole lot of damage, right? A little paint spray, maybe a little dent in the fender, nothing too serious. Okay? So then you go out and you pull out on Detroit Road. And now you're driving along a Detroit Road and you're going 30 miles per hour. Okay? 30 miles per hour. Okay? And again, unfortunately you get into an accident. Right? So while the first accident wasn't real bad, a little scrape of paint, a little dent in the fender, right? That was at 10 miles per hour. Now you're going 30 miles per hour. How much worse of a crash is it than your little fender bender in the Giant Eagle parking lot? No.
6 times. 9 times.
It's 9 times as worse of a crash. Because what kind of relationship do speed and kinetic energy have? Quadratic. So if you're going 3 times as fast, you don't have 3 times as much ability to do damage. You have 9 times as much ability to do damage. Does that make sense? Right? So now, a couple days later, in a different car, right? You get your first chance on the highway. Now you're going 60 miles per hour. Right? So, if you get into an accident going 60 miles per hour, how much worse is it than your little fender bender in the Giant Eagle parking lot? No.
36.
36 times as worse. Because what do we do with the velocity? We got to square that velocity. All right? Kinetic energy very much depends on the motion. And it's not a direct relationship, it's a quadratic relationship. All right, Monday we'll talk about potential energy and we'll do some calculations. There is some pages from the book that I would like you to read over the weekend. See if you can squeeze them in.